This is Bob Capetta, and this lesson is on symmetries. So we're going to first talk about equations or functions that are symmetric with respect to the y-axis. So what does that mean? Let's go ahead and take a look at a picture. So if I have a question like this, if I have y equals x squared, what will you notice here? You'll notice that if I folded this half of the graph across the y-axis, it would match the other half of the graph. It acts as a mirror. So let's look at some points here. We have the point, for example, 2, 4. And what is its mirror image relative to the y-axis? It would be the point -2, 4. You can look at this and you can indeed see that half of the graph is on the right side of the y-axis, half of the graph is on the left. If you'd fold them over, all of the points would match. That is symmetric with respect to the y-axis. Now we could change it a little bit. If we do this, notice it's still symmetric with respect to the y-axis. Y equals x squared minus 5. Fold over the right-hand side, it'll match. On the left, this time we have the point 3, 4, and -3, 4. You can see our mirror images of each other. But if I do this instead, so if I go x plus 1 squared, notice it no longer is symmetric with respect to the y-axis. So what do we have happening here? We have a situation that the right half of the graph does not fold over onto the left. So that's where we are. That's a basic idea. So let's look at these in terms of how we can analyze this algebraically. So let's take a look at how this is going to behave. So the first example I had was y equals x squared. Now, what does it mean for something to be symmetric with respect to the y-axis? I have a point here, which is x comma f of x. So this is x, and I want to be able to fold it over. So if that's the case, -x would be here, but I want it to match. So if that's the case, I would need this point to be -x comma f of x. Or if you like, x comma y, -x comma y. That's what we need for graphs to be symmetric with respect to the y-axis for all of those pieces. So what's our strategy to check for symmetry with respect to the y-axis? How do we check that? You're going to replace x with -x and see if the equation changes. So what I started with was y equals x squared. Replace x with -x. So we get y equals -x quantity squared, but -x times -x is +x squared. Same equation. So when we replace x with -x, the equation is exactly the same. When that happens, we can say that the graph is indeed symmetric with respect to the y-axis. It's a lot of words to write, but you get the idea. Now, the other example I looked at was y equals x squared minus 5. So what am I going to do? I'm going to replace x with -x. That's our strategy to check to see if something is symmetric with respect to the y-axis. Replace x with -x and see if it's the same. So we're going to get y equals, replace x with negative x. But again, negative x times negative x, positive x squared. Same as original. Therefore, this is symmetric with respect to the y-axis. And the other example we looked at was y is the absolute value of x. I hope it's kind of obvious if you replace x with negative x, y is absolute value of negative x, which is the same as y is absolute value of negative 1 times absolute value of x. And we just get y equals 1 absolute value of x, y equals absolute value of x. But you know what that graph looks like. You know that indeed that graph is going to be symmetric with respect to the y-axis. So replace x with negative x, and the equation is exactly the same. Now, if we look at functions, for example, if I take a look at f of x equals 3x squared minus 5, what I'm going to look at here is I'm going to replace x with negative x again, because we're going to check to see if the graph is symmetric with respect to the y-axis, which will give me f of negative x is the same as 3 times negative x squared minus 5. So f of negative x is 3x squared minus 5. You'll notice that's the same as f of x. Notice f of x is the same thing as f of negative x. So replacing x with negative x, we wind up with the same equation in essence, right? Y equals 3x squared minus 5, y equals 3x squared minus 5. This is symmetric with respect to the y-axis. Also, this function is even. So our definition if f of negative x equals f of x for all x, then we say f is an even function. And you'll notice that in many ways is suggested by the fact that the exponents are negative. So here's an example of another even function. 5x to the 4th minus 3x squared minus 7 constant, 7x to the 0. All of the coefficients can be positive or negative, but all of the exponents on the variables have to be even numbers. If that's the case, we're going to have an even function. So again, an even function will be a function that is symmetric with respect to the y-axis. Let's take a quick look at that last graph and see what it looks like. So we said this is an even function now. G of x equals 5x to the 4th minus 3x squared minus 7. Is it symmetric with respect to the y-axis? Notice, if I fold it over, this half of the graph to the right of the y-axis, fold it over to the left half, and they match. And that is an even function because f of negative x equals f of x. Now, if we're looking at something that is going to be symmetric with respect to the x-axis, take a look at that. So if you fold it over the x-axis, the points will match. Something like this, assuming I've drawn it correctly, is indicating something that is symmetric with respect to the x-axis. But I want you to notice, this is not a function. It does not pass the vertical line test. It does not pass the vertical line test. But what do we have here? Here is a point on the graph that is x comma y. And here's a point on the graph that is x comma negative y. Does that give me an idea in terms of how this behaves? Well, let's go back to the graph again and see what we have. So our standard equation there might be something like x equals y squared, which you will notice if I fold this over the x-axis, the points would match. So how do I test to see if something is symmetric with respect to the x-axis? So how to check that? You replace y with negative y and see if it's the same. If the equation is the same, then you know you have a graph that is symmetric with respect to the x-axis. So we were looking at x equals y squared. Replace y with negative y, that'll give me x equals negative y squared. Negative y times negative y tells me x equals y squared. Same equation. So this graph is symmetric with respect to the x-axis. Again, you're not going to be able to create functions that behave that way because that would violate the vertical line test. We can look at other sorts of things. Again, what would that be? 2x plus 3y squared plus 5 equals 0. Symmetric with respect to the x-axis. Because if I would replace y with negative y, I get the same equation back. How do I show that? Replace y with negative y. We're looking at 2x plus 3y squared plus 5 equals 0. Replace y with negative y. So I get 2x plus 3y squared plus 5 equals 0, same. So this graph is symmetric with respect to the x-axis. Replace y with negative y, and you get that. There is one other case for us to look at. And we're going to go back to our graph again. What if I have y equals x cubed? So where is the symmetry here? Where is the symmetry here? Well, we can't fold it just once. You can see the point 1, 1 and the point negative 1, negative 1. That's our issue. I want you to envision folding it twice. So take the right half of the graph, fold it over the x-axis first, and then fold it over the y-axis. If that happens, that's said to be symmetric with respect to the y-axis. Check that, symmetric with respect to the origin. So we see it folding over twice. Boom, 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 to match up. And what we do here is we replace both. Replace x with negative x and replace y with negative y. If the equation is the same, the graph is symmetric with respect to the origin. So our example here was y equals x cubed. Replace y with negative y and x with negative x. Negative y equals negative x cubed. So I get negative y, negative x, negative x, negative x. That's negative x cubed, which of course yields y equals x cubed. So it's the same. So this graph is symmetric with respect to the origin. Now, in the event of a function, we have another important fact here for us to look at. If I have f of x equals x cubed, and I look at the behavior of f of negative x, that of course is negative x cubed, which is negative x, negative x, negative x. That's negative x cubed, which is the opposite of f of x. Remember, f of x was x cubed. F of negative x was the opposite of f of x. So if f of negative x is the opposite of f of x, then the graph is symmetric with respect to the origin. And the function is odd. So that's an odd function. So there were 3 topics we looked at in this lesson. Symmetric with respect to the y-axis. How did we do that? Replace x with negative x. If same, then it's symmetric with respect to the y-axis. In the case of a function, f of negative x equals f of x. The function is even. And the graph is symmetric with respect to the y-axis. Our second case was to look at symmetric with respect to the x-axis. Well, replace y with negative y. If it's the same, if the equation is equivalent, then the graph is symmetric with respect to the x-axis. Can it be a function? No, you would violate the vertical line test. In all cases, except for the function f of x equals 0, trivially would be symmetric with respect to the x-axis. And then finally, symmetric with respect to the origin. Let's replace x with negative x. And replace y with negative y. If the same, then the graph is symmetric with respect to the origin. Remember, that means fold it twice. fold over the x-axis and fold over the y-axis, and they will match. In the case of an odd function, if f of negative x equals negative f of x, the function is odd. And odd functions are symmetric with respect to the origin. That'll do it.